Okay, thank you. So, yesterday I defined what it means for a group to be sofic. And so let me remind you very quickly. So we have gamma, let's say a finitely generated group, and S as above, so that's the finite generating set. Finite symmetric generating set. Then we have defined this space GS. Basically, this was the space of all directed, rooted, connected S-labeled graphs. And we have this space of probability measures on this space, and it contains the KD graph as a directed S-labeled graph as an element, right? To take the Dirac measure at this point in this space, right? And we have said that gamma is sofic, basically by definition, if there exists a sequence Gn of finite S-labeled directed graphs such that the corresponding measure that you can associate to Gn by choosing a root uniformly at random, this converges to this Dirac measure at the KD graph. Right, and more concretely, what does that mean? So what does it mean for this sequence of graphs to converge to the KD graph? Well, it means that for each fixed radius R, the proportion of points in this space, in this graph Gn, which have the property that at a radius R, they look exactly like the KD graph would look like at a radius R, this proportion of points tends to 1 as n tends to infinity. Right, so let me write this out. Right, so for all radii, the number of points, right, so the number of vertices of the graph Gn, so that Gn V as a rooted graph at radius R, so I write the restriction to R to mean the radius R around the root, is isomorphic to the KD graph of gamma S around the neutral element, right? This is also restricted to radius R. Right, so this number, well, how do I write this? So this number, let's say, divided by the number of all edges, that this tends to 1 as n tends to infinity. Okay, so this is a property that's now sort of maybe a little bit more concrete, so you can just check whether the sequence of graphs satisfies this property. And you can also start with a particular sequence and try to modify it and improve it somehow so that it has more and more properties that you would expect from the KD graph. Right, so some remarks. Right, so I said that these GNs, that they are S-labeled and directed graphs, but not necessarily do they have the property a priori that for each label S, there's a unique edge starting at a vertex with label S. Right, that's not part of the definition, and also not necessarily do they have the property that there's a unique labeled edge that ends at a certain vertex, right? But of course, if they locally look like the KD graph, then for more and more vertices, this will actually be the case, right? Because if it's isomorphic, then there's some uniqueness. Right, so if there's only a little tiny amount of vertices where this property fails, we can just add some edges or remove some edges to fix it. So without loss of generality, actually we may assume that the GNs are what's called an S Schreier graph which by definition just means there is a unique ingoing and outgoing directed edge for each label at each vertex. Right, so it really, in that respect, it really looks like the KD graph. Well, it's because of the finiteness, right? So if there are too many edges starting out, you just remove some so that there is at most one, and then you have to add a few to correct the cases where there are no outgoing, let's say. But because of the finiteness, there are exactly the same number of outgoing missing than ingoing, so that it's doable, and it's always just a small change, right? So it's the finiteness which makes that possible. Okay, so let's now, for simplicity, just assume that this set S is a list of group elements and their inverses, like this, and that all these elements are different. I mean, it's not really needed. But then what we can obtain from such a graph, which has this uniqueness property in the ingoing and outgoing edge, well, we can interpret each of the label just as a permutation, right? And so what that gives us then, right, that we obtain for each Gn a list sigma 1 through sigma n of permutations of the vertex set of Gn, which exactly follow the edges which are labeled by G1 through Gn, right? So sigma 5 would exactly move a vertex to the endpoint of the unique edge, which is labeled with G5, right? So that's very natural to consider these permutations. And so let me write this in a different way. So there exists a homomorphism now phi n from the free group. Well, maybe there are too many n's now, so let's call this number d here, right? So there's a homomorphism, right? And I should also call this d. Yeah, that I wanted that to be part of this condition, right? I mean, it's also true for the KD graph, so it will also be true locally for most of the edges, so you can just assume it's true everywhere. Well, the G1 inverse will just correspond to the inverse permutation, so I remove it from the list. Right, so what I obtain is a homomorphism from the free group on D generators into the symmetric group on the vertex set of this finite graph by just sending the ith generator of this free group to the permutation sigma I. Right, and now I want to summarize what are the properties, what is the crucial property of this sequence of homomorphisms as n tends to infinity. Right, in order to do this, of course, somehow have to keep track of all the little mistakes that occur, and then so the best way to do this is actually to introduce a metric on this symmetric group. So let's define this metric. Definition: the Hamming distance on, say, the symmetric group on X is defined so X is a set, right? Finite set is defined as follows. So you have two permutations, and you define the Hamming distance to be a normalized number of points where sigma and tau are different, right? You want to measure how different they are in terms of a metric, so that's very easy. You count the number of points where sigma of x is different from tau of x, right? That's a certain number. It's at most x. So what you obtain, cardinality of x. So what you obtain is some some number in the unit interval. Okay, and so with respect to this metric, which exactly somehow allows you to quantify that maybe on some small sets something is not quite correct, this is exactly the right metric that allows you to say what this sequence of homomorphisms will satisfy. So let me write that down. So first of all, consider also the map which I denote by pi from the free group on D generators just to gamma, where you send the ith generator to GI. Then if gamma is sofic, then you have the following property. Then there exists a sequence, xn of finite sets, and there exists a sequence phi n homomorphism from the free group to the symmetric group on this set xn, such that the first property is that, right, so if I write here, maybe I want to also mention the space X in the notation for the metric, so that we are not confusing these different metrics. So if you consider the image in the symmetric group on the space Xn, and here you compare phi of G times phi of H with phi of G times H, then this will tend to 0 as n tends to infinity. Secondly, the metric distance of phi of G to the identity permutation, that this will tend to 0 as n tends to infinity for all G which lie in the kernel of our homomorphism pi, right? So for all the G's that we don't want to see actually, because they are trivial in the group. And then there's a third property which basically says that this is a non-trivial homomorphism, right? And so you have that the metric distance of phi of G to the identity element, that this tends to 1, so it essentially moves all the points as n tends to infinity for all G that do not lie in the kernel of pi. Okay, and what I'm saying is that this is essentially obvious from the definition of soficity. Of course, you have to follow this definition carefully. But if these graphs really locally at any fixed radius look more and more like the KD graph itself, then any question that you ask, so for example, on how many points will phi of G times phi of H be different from phi of G times H, the proportion of the points where this fails is decreasing as n tends to infinity, because this is this G and H, they will have finite word lengths in the free group on D generator, so you're essentially asking for which points, what am I saying here? What? No, I think I confused. Okay, sorry, this was complete nonsense. So what is correct is that, so this is condition 1, condition 2, this does not exist, and this is condition 2. Exactly, and that's why I don't want to list it. So it's, okay, this was nonsense. So you can, I mean, if you want, you can define these phi n's also on the group gamma itself, and then the first condition is better, but this was, sorry? Yeah, there are some n's missing too. Okay, so what does it mean that G lies in the kernel of pi? That means that if you read the labels of G, then they will form a cycle in the KD graph. And so this sequence of finite graphs that approximates the KD graph will, around most of the points, have the same property. So this, the proportion of points where it actually fails tends to 0. Right, and the same argument that this second is going into the second condition. So it's really easy to see. Yeah, exactly. Well, I mean, the kernel uniquely determines gamma because it's dequotient by the kernel. So there's no more that is needed. And there's actually a theorem, and probably I should mention this. In fact, the equivalence of all these different pictures and also the systematic study of sofic groups using this permutation. This is has appeared in the work of Gabo-Edek and Andreas Thom, and so let me just write the name here to the theorem, saying that this condition that I've written here is actually equivalent to the group being sofic, right? So this is also equivalent to soficity, right? So once you have such a sequence of homomorphisms from the free group, then you can show that the group in fact is sofic, and it's not very complicated. So the vertex set of the finite graph is just the xn, and then you put edges according to your homomorphism phi n. Okay, so let me now explain yet another description of soficity, which involves no limits anymore. I mean, it will just involve one limit, but it's not a limit of numbers, it's an ultra limit of groups. And so let me say just a few words about ultra products of groups, and I will not speak about ordinary algebraic ultra products, which you might know or might not know, but it's actually the context of metric groups, so just exactly like these symmetric groups with their Hamming distance. So let Gn Dn be a sequence of metric groups, right? And you want a few conditions on the metric, so it should not just be a left invariant metric, but it should actually be bi-invariant. So you want that d of g comma h is actually the same as d of k times g, k times h, and also the same as d of k times g times k, h times k. And you want that these metrics, they all take values in some standard compact interval. So let's say we normalize it to be a unit interval. Right, so these conditions, triangle inequality, that's basically what I need for this definition. So if you have such a sequence, then you can construct a new group which reflects the asymptotic properties of this sequence as n tends to infinity. And this goes as follows. We define for some ultra filter W some element in the Stone-Jack compactification, which is not the principal ultra filter. We define a new group, so we define G omega with the metric D omega to be a certain quotient, and it's a quotient of the product of all the GNs by, first of all, a certain subset of this product. And so we want to quotient out by this, in fact, a normal subgroup of those elements that converge to zero or converge to the neutral element along the ultra filter. So Dn, right, so you have the metric Dn of Gn. This converges to zero, so the metric distance to the neutral element along the ultra filter. And what is the metric D omega? D omega, so the metric difference between two sequences, is defined to be the limit as n tends to the ultra filter of the metric difference of Gn and Hn. So it's well, some number in the unit interval. Right? So if you haven't seen ultra products, then this, I mean, you should just think of n tending to omega as n tending to infinity, and you should basically ignore the problem that this might not converge. Right? Right? So obviously it shouldn't, because there's no reason why it is always converging, this sequence. And that's exactly what this ultra filter takes care of, right? The ultra filter is a consistent choice of a convergent subsequence, right, for all sequences at the same time, right? That sounds like a miracle a little bit, but it's, well, something that well, I would like to use in this context, right? And so here it's the same thing. This means along some consistently chosen subsequence, this will actually tend to zero. But if you don't know about ultra filters, just think of this as tending to zero, and ignore the convergence problem in this at this point. Okay, so what does it give us? So we have now combined all these finite groups with their metrics into well, one object that really captures the properties of this Gn as n, well, tends to infinity. And so it's no surprise that this definition here has yet another reformulation by saying that the combination of all these phi n's, which is a homomorphism of the free group into this metric group here, actually descends to the group gamma, right? Just basically because all the elements in the kernel of pi, they will lie in the subgroup that you have quotient out. So it's exactly made in such a way that this works. Right, so hence the combinations of these phi n's, this defines a homomorphism from the free group now into this so-called metric ultra product. And if you go to the quotient gamma, then this here will exist just because of the first condition. Right, and because of the second condition, this map will be injective. Right, so it exists by 1 and is injective. In fact, it's in some sense, in a certain sense, isometric, right? If you put distances equal to 1 to all different, pairs of different group elements, that's a natural distance that you can study on the discrete group gamma, then it will actually be an isometric embedding, right? That's That's what you have. Right, so you can embed, that's the thing to remember, you can embed gamma into this ultra product. And now it's again a theorem, and it's also due to Edek and Szabo, is that the existence of such an injective map to, right, so this is now of course applied to the sequence where Gn is equal to the symmetric group on Xn, right? So the theorem is now that G is in fact sofic if and only if gamma can be embedded into such an ultra product. Yes, exactly. Gamma is sofic if and only if G can embed it into this, or Gn equal to the symmetric group. Okay. Right, so maybe I also mentioned the metric here. Right, so if you start looking at this, it's now becoming more and more natural. You have a natural way of forming ultra products of some very natural groups, like the symmetric groups, and now you call a group sofic if it is a subgroup of such a metric ultra product. Right, but these metric ultra products themselves, they are largely mysterious. So, for example, we really don't know whether it, up to isomorphism, depends on the ultra filter, or whether it really changes if you change the sequence of sets and so on. So there are all kinds of rather basic questions which, I mean, first of all, might depend on set theory, so you maybe don't want to really answer them, but maybe not, and okay, so we don't know. And the second remark is that this definition already this characterization of soficity is like a window which allows you to leave graph theory completely, right? Because you can replace these groups which have a natural and nice metric by all kind of other groups that have a very nice natural metric, and there are plenty of examples coming from functional analysis, where you look at, for example, finite dimensional unitary groups, or you can look at general linear groups over finite fields. All these groups, they have very natural metrics which come in a canonical way, and so you get all kind of other properties that are in some sense analogues of soficity, and they are also useful for some problems, useful to solve and study some interesting problems. Okay, so I will now use this characterization of soficity to prove this this first conjecture, following the work of Edek and Szabo, and then also prove the second conjecture for sofic groups. Okay, so let me remind you what is conjecture 1. So gamma is a group, K is a field, and you have A and B elements in the group ring of gamma with coefficients in the field K. And what you want to know is that if A times B is equal to 1, then also B times A is equal to 1. Okay, so I mean, let's think how we would prove that. In the case of some easy groups, like for example for the trivial group, it's completely obvious because it's just the field itself. So A times B is 1. If both are invertible, then B times A is also equal to 1. But what is if gamma is finite, right? If gamma is finite, then we can use the embedding of the group ring into the left regular representation, right, which acts on a vector space. So this is basically this, I just write it. This is basically the linear endomorphisms of the group ring. You just act by left multiplication. And so that's a matrix ring, and for matrices we know that if A times B is equal to 1, then they both have to have full rank, and then they both have to be invertible, and then B times A also necessarily has to be equal to 1. It would be a projection, but it also has full rank, right? And the full rank projection has to be equal to 1. Right, so that's very easy if the group is finite. And if the field is special, so if the field is equal to the complex numbers, then we can basically do the same trick also for an infinite group, following the technology that was introduced by Charles in his talk, because we can study the group von Neumann algebra associated to the group gamma, and so this was defined to be some span of group elements, right? It's a certain closure inside the bounded operators on L2 of gamma, right? So we have only seen it for a unimodular measure, but let me just explain this really very briefly, because that's not the interesting case that we want to study. And then there's a trace on this algebra. So the trace of A is the inner product of A applied to the standard vector sitting at the neutral element with the standard vector again. And this really behaves like the trace on a matrix algebra, right? And we can then do exactly the same argument, right? I mean, of course, I cannot explain the details, but I just tell you the story. If A times B is equal to 1 in the complex group ring, then it will also be equal to 1 in this group von Neumann algebra, which contains the complex group ring. And then B times A, or in fact lambda of B times lambda of A, is an idempotent in this group von Neumann algebra. Right? Idempotent means it squares to itself. Why does it square to itself? Well, BA is equal to BA because in the middle you have AB, which is equal to 1. Right? BA is an idempotent, but the trace of B times A is equal to the trace of A times B, because the trace is a trace, and the trace of 1 is equal to 1 in this normalization. So you have obtained an idempotent of trace 1, and then for matrices you would know that there are no idempotents of full trace unless you have the identity. And in fact, the same argument is true in any finite von Neumann algebra. And so you can conclude that B times A is equal to 1. So that's the very, very brief sketch of this result in the case when the field is the field of complex numbers. And we will basically follow the same strategy. We try to find a larger ring, a ring extension of the group ring, in which, for some magic reason, it's actually obvious that A times B equal 1 implies B times A equal 1. It's only the question, what is the nice ring that we can choose if our field has finite characteristic, right? That's something which is more difficult, right? But if the group is sofic, then we have some additional input, and that's exactly the input that we want to use now. Okay, so you have these maps from the group from FD to the symmetric group on the set Xn, and we linearize, so we also call that phi n, this to a map from the group ring of the free group on D generators. But now, just since we linearize, we have to take linear combination of permutation matrices. So we arrive at matrices with coefficients in the field K of size given by the set Xn. Right? So that's basically the linearization. Right, and now observation, or it's remark. As phi tends to infinity, so for all, let's say, A which lie now in the kernel of the natural map from the Coop ring of the free Coop to the Coop ring of gamma, we have that the normalized rank of the matrix that we obtain by applying phi n. So the rank of the matrix phi n of A normalized by the size of xn, that's again a number between 0 and 1, this actually tends to 0. Yeah, and also for any element which does not lie in the kernel, it does not tend to 0. Right? That's another statement, which is right. And why is that? Well, that's because this Hamming distance on permutations is exactly the distance that is measured by the rank of the corresponding permutation matrices, right, up to maybe a factor of 2 or something like this. Right? So if you have two permutations that look alike on a large set, if you take their difference as permutation matrices, then you will create a lot of zeros because there's a lot of cancellation. And hence the rank of this difference will be very small. Right? And so that's exactly what we are using here. Also in this linearized form, we have some control on this, on the elements which lie in the kernel of the obvious quotient map. So now the trick that we are doing is to consider now an ultra product of these matrix algebras, and that will be the ring that we are using. Right? So we define R to be an ultra product of these matrix algebras. So we are already fine with ultra products. So we take this product and divide out a certain two-sided ideal, and it's the two-sided ideal that exactly consists of those sequences, so that the rank of an divided by the size of xn, that this tends to 0 along the ultra filter. Okay, and now the proof basically has two steps. So first of all, we want that the Coop ring of gamma can map to this ring. So using the combined power of all these maps phi n. Right, and that's basically in short, that this map is well defined is basically in short by this remark, because all the elements which lie in the kernel of the homomorphism from the free Coop ring to the Coop ring of gamma, they all have this property that they have vanishing rank as n tends to infinity, so they will all lie in the two-sided ideal that we factor out. So this is a well-defined map, and the injectivity needs a little argument, but that's also true, right? Okay, so this R just plays for the argument exactly the same role as this Coop for Neumann algebra. And now there's another lemma, which now says that if you have A times B in R, with A times B equal to 1, then this implies that B times A is equal to 1. Yeah, and that's basically because you have this consistent concept of rank, which you inherit from the matrix algebras, and if A times B is equal to 1, then both have to have full rank, and that happens if and only if they are invertible, and so B times A is also equal to 1. Right? That's of course also a little argument. You need to reprove this statement that you know very well for matrices, that A times B equal 1 implies B times A equal to 1. You have to reprove it using only the concept of rank of matrices, right, or rank of elements in this ring R, right? And so that's another little lemma, and so that then finishes the proof, because if it's true in here, then it will be true for any subring. So that's the end of the brief sketch of this argument. So where have we used the sophicity? Well, we have used the sophicity to approximate our group by a sequence of finite structures, and then we have used the sequence of finite structures to using basically only the concept of rank of matrices to conclude that B times A is equal to 1. So we have used the finiteness because it allowed us to basically count how non-trivial an element is in a ring, and how far it is away from the identity, for example, and then basically B times A was at distance 0 from the identity. That's why it must be the identity itself. Okay, so that's the rough idea of the proof, and well, that's what I wanted to tell you about it. So now I somehow forgot when I started. So I have 20 minutes left, is that right? Or 15 or something? Okay. Okay, so now we want to talk a little bit about this conjecture 2. And this was the following. So you have gamma is a cube, and you have a word. Let me now write it more abstractly. You have, so that's what it means to have an equation over a cube. So you have an element in the free product of gamma with the integers. So, right, so with this new variable. And you have this non-singularity condition. So if you write this gamma, let me just write it again. You have that the sum over these epsilon i's is not equal to 0, right? So this was the non-singularity condition on the equation. And then the conjecture is that there exists a cube extension of gamma, and there exists some t, or let's say some t prime in lambda, such that omega of t prime is equal to the neutral element considered as an element in lambda, right? So just evaluating everything, you obtain the neutral element. Okay, so this was the property of this equation being solvable over gamma, right? You find some cube extension in which it is solvable, and it's very natural to consider cubes which are algebraically closed, in which every equation non-singular equation that you could study already has a solution in the cube itself. And so then it would follow that this conjecture is true for a cube gamma if you can, for example, embed the cube gamma into some algebraically closed cube, right? So that's very easy. So we only have to provide enough examples of algebraically closed cubes, and under some condition on gamma provided embedding into such an algebraically closed cube, right? And so the construction will be a bit similar as on this side. So we will use some approximation property to basically embed the cube into something which is made out of manageable pieces, matrix algebras or unitary cubes in this case, and then we can conclude. And so the theorem that is central here is the theorem of Gerstenhaber and Rothaus, which says that for all n, UN, the unitary cube on an n-dimensional Hilbert space, is algebraically closed. Right, and what does that mean? All omega can be solved in UN. So you don't even have to extend the group. It's actually already doable in the group itself, right? And so if you, yesterday I explained this analogy that if you want to prove the existence of an algebraic closure of a field of characteristic 0, you can just embed into the complex numbers, and you can use the topological properties of the complex numbers to show that complex numbers are algebraically closed, and then conclude. And here it's actually exactly the same strategy. So you have some topological group in which you embed your discrete group, and using the topology you show that equations can be solved, and therefore they can be solved over your algebraic group that you want to understand. Okay, so how do we solve equations over UN then? That's the trick that is still has to be explained. And that goes as follows. So you have such an equation with this condition, and you consider it as a map from UN to UN itself. Consider W as a map from UN to UN, mapping, well, T prime to the word evaluated at T prime. Right? And what we have to show is exactly that the neutral element is in the image of this map, because if it's in the image, then any pre-image of the neutral element will be a solution to our equation. So UN itself is a compact manifold, so we can try to find topological or homotopy theoretic reasons why this map actually has to be surjective. And that's exactly what we are going to do, and we are using the concept of degree. So the degree of some map, so let's say F is a map between manifolds. The degree of F is exactly is a certain number, is a certain integer, such that on the top dimensional homology of this manifold, this F star is actually equal to multiplication with n. Right? So if you study, for example, the unit circle, then the identity has degree 1, and raising in the complex number to the nth power has degree n. So in that case, it's exactly the binding number, but it can be defined for any manifold. F, it's the map induced by F on the homology. And so the properties are the following. So if you compose two maps, then this is just the degree of F is just the degree of F plus the degree of G. No, what? It's the product, yes. Okay. Then secondly, if F is homotopic to F prime, then the degree of F is unchanged. Right, that's easily seen from this definition. So if you have a map F, then it induces a map on the homology of this manifold. And in the top dimension, there is a group which is just the integers itself, given by the top dimensional homology class. So I assume it's oriented. And so this is now a map from the integers to the integers, so it must be given by multiplication with a number. And so that's exactly this number n. And so the third property is the following. If F is not surjective, then the degree of F, the degree must be 0. Right, and the reason for this is that if the map is not surjective, then there's a little hole in the image, right, and then you can basically, using a continuous process, continuous homotope this map to some map that takes values only in the lower dimensional part, right? It will not hit anything in the top dimensional homology, and then this n must be equal to 0. Okay, so that's basically, I think, all that we need. There's another description that's maybe also important for the argument, that the degree can actually be computed by counting with orientations the number of pre-images of F. Right, so degree of F is the number of pre-images of some x in M under F, right? So this is true generically. So for most of x's it will be true, counted with multiplicities. Right, so since the manifold is oriented, sometimes the orientation is reversed and then you have to count it with a minus sign. Okay, so I will not say more about this concept now. So let's study our maps that we want to study. So the map is given very concretely. It maps T prime to G1 T to the epsilon 1 up to Gn T to the epsilon n. That's again a unitary matrix. We just take the product of these matrices. And these GIs, they are just arbitrary constants. So since the unitary group is connected, we can, for each GI, we can choose a path that connects it to the neutral element. So this map W is homotopic to the map W prime, let's say. The W prime of T prime is exactly T prime to the sum over these epsilon i's. Right? And the homotopy is a very simple thing. You just choose a path from each of the group elements, connecting it with the neutral element, and you basically obtain a continuous family of these maps W that starts here and ends exactly with the map where all the constants are gone, and then you just obtain the sum of these exponents. And so it's now very easy to compute the degree of this map, because the degree of this map W prime can be computed as the number of pre-images of a generic point. So you just have to ask yourself how many roots does a generic matrix have. And so, well, that's very easy for, on the unit circle, if you have a generic number on the unit circle, then the number of roots is exactly given by this exponent. So now you have n numbers on the diagonal. So this degree allows, this degree is just this number sum over the epsilon i's to the n, because you have n choices for each of the eigenvalues, basically. Right, generically. Right, and so definitely, no matter what this is exactly, this is not equal to 0. And so we can combine the information that we have. The degree of this map is not 0. It's homotopic to W, so the degree of W is also not 0. But then W must be surjective by this third condition. Right, so combining all the knowledge that we have accumulated, W is surjective, and that's exactly what we needed to show. Okay, that's the argument of Gerstenhaber and Rothaus. That was in the late 60s, and they were also motivated by this conjecture. But having the group UN, the only thing that they could conclude now is that all the groups that, for example, can be embedded into UN, they satisfy this conjecture, and more generally, also groups which are residually finite. And so the only thing that we can add now is that it's also true if the group is sofic. Okay, and that's now not very complicated anymore, because consider a sofic group. Consider a sofic group gamma. We only have to, in a suitable way, embed gamma into some group made out of these unitary matrices. So how do we do this? Well, we have gamma, well, the free group with phi n mapping to the symmetric group on the set xn. But this group of permutation matrices, of course, it sits inside the unitary group on the Hilbert space of dimension equal to the size of xn. And so that's a metric group, and here we also want to choose a natural metric. And so we take the normalized Hilbert-Schmidt distance. So we define, so if we have unitaries u and v, we define a distance function, and it's the following. So we take the, well, let me write it out. It's u minus v star u minus v, like this. So the square root of the trace of this absolute square of the difference of u minus v, the difference, and so the point is, so let me write this here, is that the restriction, so this is a metric on u of the Hilbert space of dimension size of xn, and its restriction to the symmetric group as a subgroup is almost the Hamming distance. So it's not quite the Hamming distance, but it's up to universal constants not depending on the size of xn. This is just the Hamming distance itself. So what we obtain using this metric on u on this unitary group is a metric that extends the metric coming from the Hamming distance. Is up to constants Okay, so what does it mean? So that means that this group gamma, it embeds into this ultra product of symmetric groups, right? So here we had this a certain normal subgroup that we divided by in order to define this metric ultra product, and here there's then a natural homomorphism to the product of these unitary groups by quotient out by some group n prime, and n prime is now just the same as for the symmetric group. So it's just a sequence of unitaries which along the ultra filter are getting closer and closer to the identity transformation on this Hilbert space. And so, because these metrics were compatible, that's exactly the part here. This map is actually an injection, right? That's important in this construction, and it's you basically want that if you have a sequence of permutations and it is in this group tends to 0 in the Hilbert-Schmidt distance, then it already tends to 0 in this metric in the Hamming distance on the symmetric group, and that's exactly what is ensured by the compatibility of these metrics. So you can embed gamma into this metric ultra product, and so I claim that it's completely obvious that if you can solve all the equations in UN, because Gastenhaber and Rothaus showed us how that goes, it's also true for this group. And the reason is simple. if you want to solve an equation in this metric ultra product, you just interpret it as a sequence of equations in these individual groups UN, and you choose a solution in each of the groups for each n, and then basically the image in this quotient will be a solution to your original problem. So that's that's how the argument goes. Okay, so I'm finished with the argument, and the time is also up. So thank you for your attention.
So questions?
Well, no, I mean, you need this concept of degree in order to transfer the solvability from this very simple equation to this other equation. So, I mean, it would be absolutely amazing if one could do an argument like this for an infinite dimensional group, right? Where you don't have to deal. I mean, you have no good concept of degree, right? For example, for just the unitary group on a Hilbert space, or the unitary group in some of these group phenomenal algebras. Maybe that's true, but it's definitely not true by this argument, right? It's more complicated.
No more questions? Okay, then let's thank the speaker again. And soon we have the problem session.